Today we are going to discuss about a new section which is known as heat engine. Heat engine. What is a heat engine? A heat engine is something which convert heat energy to mechanical energy. Heat energy to mechanical energy. So we use heat energy to produce a mechanical energy or mechanical work. For a heat engine, there are different parts. And the main part is known as a high temperature region known as source. Let it be at T1 Kelvin. It's a high temperature region known as source. Another one is the working substance. Working substance. Actually, that will be a gas, and that gas will take heat energy from the source so that it can perform some external work. And you know one thing, it is impossible that all the heat absorbed is being converted to work. It is impossible that all the heat absorbed is being converted to work. So part of the heat will be remaining with the substance, working substance. So the rest heat or the remaining heat is to be given out to a region, and that region is known as a low temperature region, and that is known as a sink. Previously it was a high temperature region. High temperature region was source and low temperature region sink. Let it be at T2 Kelvin. Let it be at T2 Kelvin, right? Now what actually happens is, part of like this working substance, which suppose it is in a container, and that container will be in contact with the high temperature source for a long time, and the heat will be absorbed slowly. See, what I am saying is only an ideal functioning. It's not what practically observed. It's something ideal functioning. So the working substance will take, suppose Q1 amount of heat from the source. Suppose it is taking Q1 amount of heat from the source and it's delivering some work. Suppose it's delivering some work, and I told you the entire heat cannot be converted to work. So the remaining part will be given back to the sink, or will be given to the sink. This is what actually happening in a heat engine. Now what happens? If I use the conservation of energy here, we have the total heat taken is Q1, and in that W amount of work is being delivered, and the rest heat is given to sink. So Q1 will be equal to W plus Q2. This is the law of conservation of energy. Now what will be the equation for the work done? Work done will be equal to Q1 minus Q2. This is the work done. Now I'm going to give you an information about a peculiar term known as the efficiency of a heat engine. Efficiency of a heat engine. Efficiency of heat engine. Generally, it is represented by the symbol eta. Basically, efficiency is something like what we got divided by what we give. What we got is the work here, right? Our advantage is work. And our expenditure for it is heat Q1. So that advantage divided by our expenditure. Something like that. That is what the efficiency is. W by Q1. So it can be written like Q1 minus Q2 by Q1, or equal to 1 minus Q2 by Q1. This is actually the equation for the efficiency offered by the heat engine. Now, one another equation for efficiency is there. That is T1 minus T2 by T1. How this relation we are getting, I will explain it later in the Carnot cycle. Now you just believe there is an equation for efficiency T1 minus T2 by T1, where T1 is the temperature of source, T2 is the temperature of the sink, and definitely the temperature should be given in Kelvin scale. It is must that temperature is given in Kelvin scale. It is must. You cannot accept that, or you cannot give any relaxation about the unit of temperature. It should be in Kelvin scale. So it can also be 1 minus T2 by T1. See, I told you one thing. What? Q2 can never be 0, right? See, I will give you some star points. Q2 is never 0. Why? Q2 is never equal to 0. Why? Q2 is never 0. Why? Because nature itself will not permit that the entire heat is converted to work. It is not possible that the entire heat is converted to work. So Q2 is not 0, never. Q2 is never 0. If Q2 is never 0, W is never Q1. If W is never Q1, efficiency can never be 1. That's it. Q2 can never be 0. So W can never be Q1. So efficiency can never be 1. So it's not possible that efficiency is never 1. Or it is impossible to construct a 100% efficient engine, efficient heat engine. It is impossible to construct a 100% efficient heat engine. Nature do not allow that. And if eta is never equal to 1, I should say T2 by T1 never equal to 0 implies as T2 can never be 0 Kelvin. So this is one another way of saying that 0 Kelvin is an impossible temperature to reach. It's impossible to reach 0 Kelvin. Actually, from kinetic theory of gases, we understood what 0 Kelvin is. 0 Kelvin is that temperature at which the entire motion ceases or entire motion stops. Such a temperature is not possible at all. Now, if I say one example like T1 equal to 1500 Kelvin and T2 equal to 500 Kelvin, say, for example, what you are expecting the efficiency to be? It is T1 minus T2 by T1, that is 1500 minus 500 will be 1000 divided by 1500, that will be 2 by 3, that is equal to 0.67, or efficiency is equal to 67%. Isn't it? So with a temperature 1500 Kelvin at the source and 500 Kelvin at the sink, this is the maximum efficiency that we can expect. This is the maximum efficiency that we can expect. And even if we wish to get that maximum efficiency, look at it. Even if we wish to get that maximum efficiency, there are so many challenges that we are going to face. What are those challenges? I will repeat. Even if we wish to get that maximum efficiency, which is not 100% efficiency, it is the 100% of the expected efficiency. So this is the expected efficiency, and I want to get the 100% of the 67%. Even if you wish that, there are so many challenges that you are going to face. One, as you take heat from the source will start to cool down. And as we dissipate heat to the sink will start heated up. Means what? T1 will be reducing and T2 will be increasing. That T1 minus T2, the difference will be decreasing. So that's a challenge. And second thing, if you are taking heat from the source, the working substance is taking heat from the source, the working substance, it may get heated up, or there is possibility that there is a kind of conduction happening throughout the side walls of the container of the working substance. All these are possibilities. There may be loss due to radiation, there may be loss due to heating up of the gas, there may be loss due to friction. All those may be the challenges about the working substance. And if the heat is dissipated to the sink the sink may get heated up. So the source may get cooled down, the sink may get heated up, there may be loss of energy through the working substances. So if any of this happens, we cannot expect to get the maximum or the 100% of the expected efficiency. So that's a challenge. So how can you deal it? Definitely, practically, you cannot deal it. You cannot even imagine about getting 100% of the expected efficiency. See, I will repeat, 100% efficient engine is not possible. Nature do not allow it. And suppose some engineer is expecting that I must get 100% of what the expected efficiency is. Even he cannot. It's not possible that he is getting 100% of the expected efficiency. Suppose someone is imagining an engine, right? Suppose someone is imagining an engine which is capable of giving 100% efficiency of the expected efficiency. 100% of the expected efficiency. We call that engine a Carnot engine. So Carnot engine is not a 100% efficient engine. Carnot engine is not a 100% efficient engine. 100% efficient engine is impossible to take place. Carnot engine is that engine which can give the 100% of the expected efficiency. For that, for an engine to be a Carnot engine, there should be 3 requirements, or you can conclude it as 2 requirements. 1, source should never cool down. Sink should never heat up. Means both source and sink should have infinite thermal capacity. Source and sink should have infinite thermal capacity. Second thing, working substance should be a perfect gas which not having any kind of friction like that. And okay, third thing I can say, the platform which supports the working substance or the container in which the working substance is should be a perfect insulator of heat energy, that the heat is not wasted by conducting it to the surroundings. So source and sink should have infinite thermal capacity. The gas should be a perfect gas. The working substance should be a perfect gas. The working substance should be supported by a perfect insulating stand. These are the requirements that an engine can be a Carnot engine. Okay. So that's all that's all the class about engine and the basic functioning of the engine. Don't forget to subscribe the channel and to press the bell button. We will be continuously discussing about the various topics in 10 minutes about physics of +1 and +2 classes. Okay. All the best. Thank you.